Okay, here we go. So March 15th, 21. So we are under a month away from the end of class. It's actually 4 weeks from today. 4 weeks from today will be the last lecture we have for this semester. It's crazy how fast it's going by. So let's just go over a few things quick. So lab assignment 4 is due Wednesday, March 17. Well, that's the case from my lab, but I think John said he extended it as well. So that should be consistent. And then I believe that we have assignment 5 due Friday, right? March, what would that be, 19th? Just check, verify that here real quick. Make sure we're all on the same page. And course outline. Yeah, cool. Yeah, so assignment 5 is due Friday. And then we have lab assignment 5 due March 29. We have assignment 6 due April 2nd. And the stuff for assignment 6 is what we're starting today. So that's going to be, this is going to be lecture 12/13. So lecture set 12/13. And then we only have one quiz left, which is now on the 26th. So that is not this Friday, but the next Friday. So Q3, March 26, 21. And then that's going to be lecture set 7 through 11. So that's two-way ANOVA through to Kruskal-Wallis testing. So, I mean, it's quite a bit of material to cover, but the quiz will be the same length as it was in the last 2 cases. Or maybe like kind of an average of that. All right, so that is where we are at in the course. In terms of material covered, so just a quick recap here. We have seen 1/2 sample inference. We have seen one-way ANOVA, CRBD, two-way ANOVA, and then we have seen non-parametric statistics. Okay, and like in the non-parametric statistical part, we just talked about alternatives to 1 sample and 2 sample inference and the one-way ANOVA. So today we're starting simple linear regression, which is my favorite. Well, regression in general is my favorite topic in the course. Yeah, I like the non-parametric stuff a lot, but this and the non-parametrics are definitely my favorite parts of the course. This lecture set number 12 is mainly review of what you saw in 151, but we're going to go into a little more detail. We're going to see lots of illustrations of the different concepts. We're going to talk more about model development, the idea behind what we're trying to do when we perform linear regression. And we're going to look at some of the simpler things you can do with a regression model, and then some of the more complicated things in terms of inferential procedures that you can do with the regression model. I'm hoping that we will be able to do most of this over this week. I think based off the course outline, we are in the week. Yeah, so if we finish most of this week, then we're actually back on track with the outline, which is reasonable. Usually it takes me about a week to 4 lectures to do SLR. And then we have the remaining time to do multiple linear regression, which will be more than enough time to kind of get through everything. And then hopefully on the last day of class, we'll have some time left over just to kind of summarize things and kind of go over what to expect on the final and the different topics we covered and that sort of thing. I'll get some practice problems up for Q3 in the next couple days. And other than that, we'll just, keep mowing through. We're getting closer. The number of assignments is dwindling. We're getting near the end now. All right, so simple linear regression. We're going to talk about what it is. We're going to talk about why it works the way it does. We're going to talk about how you actually fit a regression model. We're going to talk about how you use it, how you evaluate it, and then how you can assess the parameters of the model from an inferential point of view. So it's a pretty jam-packed lecture in terms of the material that we're going to look at, but a lot of it should seem fairly familiar. Again, this is supposed to be a review of what you saw in Stat 151, but with a little bit more depth. All right. So what is linear regression in general? Linear regression is actually a modeling technique that we use to link what we call the response variable to a set of explanatory variables. So there isn't actually a limit on how many explanatory variables you can have in your data set. So you can have y, which is the response, be a function of up to, let's say, k different explanatory variables, where k can be 2, 3, 4, 5, 6, 7, etc. Simple linear regression, which is the focus of this lecture set, is a specific case of linear regression when you only have one explanatory variable. So the reason it's called simple linear regression is because you only have y being related to x directly, and there's no other explanatory values being utilized in the model. Right? So simple refers to the fact that there's one explanatory value. All right. The simple linear regression model states that the response variable y is equal to beta0, which is what we call the y-intercept, plus beta1, which is called the slope, multiplied by x plus epsilon, which is an error term. Okay, so the idea here is we are saying y is a function of a constant plus a constant multiplied by x, which is your explanatory value, plus some error. The error term is effectively saying that we don't expect the relationship to be perfect. We always expect the points to deviate from the line at least a little bit. It also introduces a distributional assumption on the parameters of the model. So you can see here that the epsilon term is normally distributed with mean 0 and constant variance. So a lot like the ANOVA model that we had talked about earlier, and actually you can show that one-way ANOVA is a special case of regression. We can show here that yi is normally distributed with beta0, beta1 xi, comma, sigma squared. So basically, when we utilize a simple linear regression model, we are making the assumption that the response variable is normally distributed and the mean of that distribution changes with each value of x according to the parameters in the model. But the variance is constant across all of those values. Okay, when we utilize a simple linear regression model, we make 4 assumptions. We assume that it's actually reasonable to fit a straight line model between the response variable and the explanatory variable, right? Like basically what we're saying here is it's not going to be reasonable to fit a straight line model to data that's not that's curved, for example. So for assumption 1, we would evaluate using a scatter plot. Okay, so we would have, for example, okay, so let's say that this is going to be 0. This is the x. This is the y. Right now, we would look at the scatter plot, and we would have our points. Maybe I shouldn't use x's since. Okay, so we would have our points on the scatter plot. Maybe something looks like this. Okay. And basically what we're asking is, if I was to put a line through these values, would that be reasonable? Does it appear like the relationship between x and y is in fact linear? So this would be an illustration of a data set where fitting a straight line would be reasonable, because you can see that as X increases, Y increases following a straight line relationship, right? Whereas something that looks like this, right, for example, that would not be reasonable, because that's very clearly not a straight line relationship. That's more of a parabolic relationship. So the first assumption we can simply validate using a scatter plot of the raw data itself. Okay, now the second and third assumptions, those would have to be validated using residual analysis. And we'll talk a bit about that a little later in the lecture set. But I want to go over the idea here. Okay. The second and the third assumption is basically assuming that we have a true relationship between Y and X. Okay, so this is going to be capital Y. This is going to be capital X, representing the population of interest. We're going to have some straight line model that relates Y to X. Okay, so maybe it looks something like this. Okay, so the equation of this line is Y is equal to beta0 plus beta1 X. Right? So we are making the assumption in 1 that there is actually a straight line relationship between X and Y. So Y is a linear function of X. And from a sample point of view, we can evaluate that using a scatter plot. Now, for the normality and the constant variance assumption, what we are assuming is that for each value of X, so let's say that this marker here is X1, this point on the line is a normal distribution okay? And each time you change the value of X, you get the same normal distribution. So I'm just going to move this up now. Oh, okay, that didn't really work. So I'll just sketch it. So every time you change the value of X, you have the same variance, but you have a slightly different, you have the same variance, but you have a different mean. So you can see the mean is shifting with the value of X. Right? So all of these distributions have the same variance. Right? But they have a different mean. Okay. So that's what we are assuming when we fit this linear model to represent the relationship between X and Y. We assume that it's actually reasonable to use a linear model. Like you wouldn't want to use a linear model if the data isn't linear, or if Y isn't linear with X. And then the second part of it is you're making this distributional assumption that the mean of the distribution changes with each value of x according to beta0 and beta1, but every single distribution has the exact same variance. So sigma is constant for all of the normal curves. Okay, and then just a real quick note here for this is just this is the SRS assumption. Okay. Any questions? Okay, so we are assuming that there is a straight line model that relates the population of X to the population of Y, or it's one population with two, that relates the values of X to the values of Y in our population of interest. Okay, so how do we estimate the parameters of that line? So in our original studies, we would have, for example, a hypothesis test where you would ask, is mu greater than some number? So H0 mu equals 14 versus HA mu not equal to 14. And then you would estimate mu using a sample of values. So you would find the sample mean and the sample standard deviation from the sample that we have collected. It's the same idea for the regression line. So we're going to take a sample, and from that sample, we're going to compute an estimate of beta0 and an estimate of beta1. Those estimates are called B0 and B1. So little b0, little b1. So little b0 is the y-intercept estimate, and little b1 is the slope estimate. And those are computed using sample data. The little x here, this should be an xi. This is the observed value of the independent variable. Okay, so that's just the xi value in our data set. And the yi hat, which is shown here, is saying that based off of x and the sample, or based off of x, b0 and b1, we now have an estimate of the value of y that we can that comes from the line that we are fitting. Okay, so the hat on top of the y means estimate of the population values of y. So to find the estimates for B1 and B0, so what I mean is to find the actual equations that we use to calculate B0 and B1, we're going to use what's called the least squares criteria. The least squares criteria says that the best fitting line is the one having the smallest possible sum of the squared errors. Okay, so the error term is the same thing as a residual term. So you can see here that the error term is the true value of y, or yi from the data, minus the estimated value from the regression line. Okay, so this is the EI value. And the same thing as a residual. Okay, so this becomes yi minus b0 plus b1 xi. The least squares criteria returns the values of b0 and b1 that make equation 3 as small as possible. Okay, so we want equation 3 to be as small as possible, and whatever value of b0 and b1 we get out of that will be the estimates we use to calculate b0 and b1 from our sample data. Okay, so we can show that the values that minimize the least squares criteria are b0 equals y bar minus b1 x bar, and b1 equals sxy over sxx, where sxy is shown in the second row of the table below. It's the sum of the product of the differences between each value of x and its mean. And sxx is simply the sum of the square differences between xi and its mean. So this is basically just, these are basically just numerators of the variances and the covariance estimates for X, Y, and XY respectively. Right. Okay, so the following scatter plot and data set give the midterm mark received and the number of hours of sleep 15 university biology students got the night before the midterm. Okay, so here's our scatter plot of the sample data, and then here is our sample data in the table next to that scatter plot. So these are the xi values, and these are the yi values. Okay. We want to know what is the simple linear regression model, or the estimate of the simple linear regression model that relates midterm mark to sleep using the that relates midterm mark to the number of hours of sleep. And in the table below here, we have some summary statistics based off of the values in our data set. In particular, we have an illustration of how you would calculate SXX and how you would calculate SXY. So you can see that we have our XI values in the first column here. The mean of the XI values is found in the normal way, and it's equal to 5.52. So then we have 4.6 minus 5.52. Then we take the square of that difference, which is negative 0.92 squared. Then we have 8.5 minus 5.52. We take the square of that, which is 2.98 squared. Then we have 3.2 minus 5.52. Take the square of its difference, which is negative 2.32 squared. And we do that for every single value in the data set. And then we sum the square differences. So this value here is SXX. Right, now we do a similar thing for SXY. So we have all of our Y values shown here in the fourth column. We find Y bar in the normal way, so that's 71.8. Then we take the differences between each observation and that mean, and then we multiply that by the difference of XI and its mean, and we get 3.496 for the first observation, 33.376 for the second, etc. And then we sum all of those, and that gives us SXY. Okay, so these are illustrations of how to compute those two values. The means, we shouldn't need to see an explanation of that because it's just the sum of the values over n. Okay, so when we look at the data in the scatter plot, again, what we're asking here is, does it look like if we were to draw a straight line through the data set, that seems reasonable, right? So does an SLR model seem reasonable? Okay, well, when we look at the data, let's suppose that we just pluck a line down on it just randomly. Something looks like this. Okay, well, we can see that there's certainly no curvature in the data. There is a bit of a weird dispersion. It almost looks kind of like an X shape or like a Y. So there's a bit of a break off at one point. But in general, the points seem to follow this straight line pattern. So we can assume that the first assumption is there's no evidence to suggest that the relationship is not linear based off of the scatter plot. Okay, so all right. So with that being said, we can now go ahead and calculate the estimates of B0 and B1 to build our estimate of the regression line. Essentially, what we've determined here is that using a straight line model or the regression line is reasonable because it appears that Y is linear with X. All right, so we have SXX and we have SXY and we have the means. So again, the goal here is estimates Beta0 and Beta1 in Y equals Beta0 plus Beta1 X. Okay, so construct yi hat equals B0 plus B1 xi. All right, so to do this, we have B0 equals y bar minus B1 x bar, and we have B1 equals SXY over SXX. Okay, so B1, we obviously have to do this first because we need it to get B0. So this is going to be 77.544 divided by, oh no, sorry, 457.66. Divided by 77.544, and that's something in the area of 5.092. Okay, so now we can do B0. So this is going to be y bar, which is 71.8 minus 5.902 multiplied by 5.52. Okay. And that's somewhere in the area of 39.221. But I'm just going to check those real quick. Oh, yeah, pretty good. Okay, so therefore, the regression equation is given by yi hat is equal to 39.221 plus 5.902 xi. So this is the regression equation for the data set that we are working with. And again, all that we really are doing here is we're just estimating beta0 and beta1. So those are the model parameters. And we have our estimates, and then we can plug them into our regression line. All right, so on slide 11, we have the fitted line for our actual data set. So the equation of this line here is the one that we just found. So this line is 39.221 plus 5.902 xi. All right, any questions so far? Okay. All right, so what can we tell from the regression line? Well, first off, when we look at the scatter plot, the indication is that it's a positive relationship. So we define a positive relationship as being one where an increase in x causes or relates to an increase in y. Okay, so as x gets bigger, y gets bigger. So that's a positive linear relationship. The opposite would be an increase in x leads to a decrease in y. So as x gets bigger, y gets smaller. That would be a negative linear relationship. So the scatter plot indicates a positive linear relationship. The more that you sleep, the higher your midterm mark. The regression line obviously agrees with this, and beta and B1, the slope, is the value that indicates whether the relationship is positive or negative. So B1 is a positive value, which indicates a positive relationship, right? So B1 is positive, therefore it is a positive relationship. Now, in particular, what B1 is telling us is that a student can expect to receive a 5.9% increase on their midterm for every hour they sleep. So recall that B1 was equal to 5.902. Okay, so B1 is interpreted as a 1 unit change in Y for a 1 unit increase in X. So this is saying for every unit X increases, Y changes by positive 5.902. Okay, so that in the context of the problem is saying every additional hour you sleep leads to an expected increase of 5.9% on the test. B0 is the expected grade if you get 0 hours of sleep. Okay, so B0 in general, B0 is the value of the expected value of Y when X is equal to 0. So it's always the expected value when X is equal to 0. So in this particular problem, B0 is telling us that a student that does not sleep the night before the test should expect a grade of 39.221%. Sorry, any questions about the interpretations? Right, so one of the fundamental uses, one of the main ways that we use a regression line is to make a prediction. Now, a prediction using a regression line is actually a very straightforward process. You take a value of X that you're interested in studying and you plug it into the line. So for example, what grade do we expect a student who only slept 4 hours the night before the midterm to receive? So we have yi hat is equal to B0 plus B1 xi. So this is going to be 39.221 plus 5.902 xi. Okay, so plug xi equals 4 into model. This gives yi hat is equal to 39.221 plus 5.902 multiplied by 4. And that gives us 62.83. Okay, so therefore, we expect a student that slept 4 hours the night before the test to receive a grade of 62.83%. Okay, so as I mentioned, prediction is one of the fundamental usages of the simple linear regression model, or of any regression model for that fact. You know, in a lot of cases, you're trying to kind of look into the future with these things and determine where something is going to go. One important consideration that we have to make when we use a linear model for prediction is we have only observed values of X within a certain range. So for example, in the sleep/midterm mark illustration, our values of X exist between about 1.5 and 10.5. So the student that slept the least only slept an hour and a half. The student that slept the most slept 10 and a half hours. So we have only observed the linear relationship between 1.5 hours and 10.5 hours. We don't actually know if the relationship is still linear outside of that range. So if you were to start plugging in, say, values of X equal to 13 or 14 or maybe 15, you might start to receive marks like Y is equal to 102% or Y is equal to 110%. And clearly that's not a reasonable estimate, because you can't, on most practical tests, you can't score over 100. I mean, there's always bonuses and things like this to consider, but on a standard test where you don't have bonus questions, 100 is the highest possible mark. So in our observed range, we have a bound on the grades between about, I don't exactly remember what it is from the scatter plot, but we're observing marks that exist between the natural range, between 0 and 100. And we're observing a number of hours of sleep between about 1.5 and 10.5. So if we start to plug in values that exist outside that range, we don't know if the relationship is still linear. So we could be using a linear model to make a prediction outside of what we have observed, when we really shouldn't be using that model anymore because the relationship is no longer linear. And that is the idea behind extrapolation, which is the practice of predicting outside what we have actually observed. And again, the issue here is that when we do this, we don't know if that relationship is still intact. So we could be using a linear model to make a prediction when the relationship actually becomes, say, curved or something like this outside of the range that we have actually seen. And if you think a little bit more deeply about the problem that we are considering, so here's our scatter plot. Right? So we observed a linear relationship, right, between Y and X. So let's say that this is around 10, here's 0, and then let's say that 100 is about here. Okay? So these are test scores now. The reality is that at some point, if it's a positive relationship, it has to flatline. Because, and I mean, it might not flatline with number of hours of sleep, but there has to be an observable bound on the highest score that you can observe on the test. So you know that once you start to predict outside of the range of 10 and you start getting marks that are over 100, it isn't possible. So again, this is another illustration of what our particular relationship might look like. Instead of it being linear after 10 and a half, it really is going to probably be like a flat line, because you can't get over 100% on the test. All right. I mean, the other thing to keep in mind too would be, you can't plug in values over 24 either, right? Because that wouldn't make any sense unless you slept. Yeah, exactly. Like, I mean, depending on the context, like what if you plugged in 30 hours? So that would it would mean you probably either slept through the test or you've been asleep for a day and a half. So it just doesn't become, it becomes unreasonable after a while. Okay, so now the next topic. So what we've seen so far is the definition of the model, the idea behind using the model, so the assumptions of the model and what we assume to be true about the relationship between the data. We've talked about the form of the estimating equation and how to find B0 and B1, and we looked at how to use the equation for prediction. The next thing that we're going to talk about is how we can assess the fit. And what I mean here is, if you fit a model to a data set, how do you know it's a good model? So how do we know that the SLR model that we have fitted is actually usable or reliable? What kind of information can we find that explains the value of that model? So we're going to talk about a few things. One of the concepts that we're going to talk about is residual analysis for assumption verification. So we know that in addition to the linearity assumption, we also assume that the residual terms or the error terms are normal with constant variance. So we're going to want to verify those, because if those don't hold, then we're fitting the wrong model. The other thing we can do is use what are called diagnostic measures. And diagnostic measures are basically statistics that explain how well the model fits the data. So the main diagnostic measure that we are going to look at is called the coefficient of determination. The coefficient of determination is essentially a value that exists between 0 and 1, where 0 would indicate no fit or very poor fit, and 1 would indicate a perfect fit. The coefficient of determination is related to what is called the correlation coefficient, and we'll talk about that in a little bit. But it's based off of an algebraic decomposition of the sum of squares. So this is going to look very similar to what we saw in the one-way ANOVA case. So when we use a simple linear regression model, we can break down the total variation or the total sum of squares in the response variable into two components called SSE and SSR. So our total sum of square is the sum of the yi minus y bar squared. So this is actually the same thing as SYY. So those are equivalent. The sum of squares error, we actually saw a definition of this before. This is the same thing as the sum of the EI squared. Okay, and then we have sum of squares regression, which is the difference between the predicted values of y from the regression line and the mean of the sampled values of y. So we have SST is equal to SSE plus SSR. Okay. All right. Now, the values of SST, again, SST is the same thing as SYY, so that can be computed using the same formula shown when we introduced B0 and B1. SSR, which is shown next to it, this is actually equivalent to SXY squared divided by SXX. Okay, so those are the same thing. The coefficient of determination is simply a ratio of SSR to SST, or equivalently. The coefficient of determination is a ratio of SSR to SST, and that's equal to 1 minus SSE over SST. All right, so we know that SST is equal to SSR plus SSE. So R squared is just taking the sum of squares regression part and dividing it by the total sum of squares in Y. So we're basically just computing the proportion of Y that is explained by the regression line. And again, sorry. So it's equivalent to SXY squared over SXX. Cool. Right, so the R squared is simply a ratio of SSR to the total variation in Y. So it's basically just measuring the proportion of Y that's explained by the fitted regression line. Right, so it's going to take, naturally, you can see based off of what it's, the decomposition, that it has to exist between 0 and 1. And again, when it's close to 0, that means that the regression line is basically explaining no information about the data. So the fit is very poor, and probably we shouldn't have used a linear model in the first place. And if it's really close to 1, that basically means that every single point sits exactly on the fitted line. Now, it turns out, or it works out, that r squared, the coefficient of determination, is actually just the square of the linear correlation coefficient. Okay, so the linear correlation coefficient is shown here, and you can see that this here is equal to sxy divided by the square root of sxx times syy. Okay. So if you square this, you get sxy squared divided by sxx syy. Okay. And if you consider that r squared is equal to SSR over SST, then this thing is going to be SXY squared over SXX divided by SYY, which is SXY squared over SXX times SYY. Right? So you can see that it's true in multiple ways. The relationship between them is that if you have r, you can easily compute r squared by squaring it. And if you have r squared, you can just take the square root to get r. Now, r squared is actually a diagnostic measure that explains how well the line is fitting the data. R, the correlation coefficient, is not truly a diagnostic measure. It's a measure of linear strength between X and Y. So R can be computed without the regression line, which would imply that R squared can also be computed without the regression line because you can just square it, right? But regression line. So it's not actually a diagnostic measure, but if the linear strength between X and Y is strong, so if R is really close to 1 or -1, then it would make sense that fitting a straight line is reasonable because one of the assumptions of the model is that the relationship is linear. Okay? Do you see what I mean? Does that make sense? Any questions? So we can use R to assess the reliability of the model because, again, if R is really close to -1 or +1, that indicates a very strong linear relationship. And if we have a really strong linear relationship between Y and X, then it makes sense that we would fit a straight line model to that data. But R squared is truly a measure that evaluates the fit of the model. Whereas, again, R squared is actually just a measure between X and Y directly. Okay, so on Wednesday, we'll pick up with a recap of the diagnostics, and then we'll look at a few examples of how to compute those in the context of our sleep data set. And then we'll continue to move on with the material in this lecture set. So if you guys have any questions, as always, please let me know. And otherwise, I will talk to you on Wednesday afternoon. No worries.